Lesson 4.1, polynomial functions. So your book starts talking about power functions that take the form f of x or y equals ax to the power of n, where a is what's called the leading coefficient, and this power n right here, well, you need a non-zero real number for a polynomial, or sorry, for a power function. Now, for a true polynomial, you want this power to specifically be a whole number, right? So like positive integers, right? So it could be x to the 1, 2, 3, right? Now, you don't want negative powers of x because that turns into a fraction, which would no longer be a polynomial. Maybe a power function, but not a polynomial. Okay? And you also don't want fractions because that like a 1/2 power could be like a root, right? And that would not be a polynomial. Right? So we need whole numbers here. Right? And so a is the leading coefficient, n, this power is the degree, and if there is a positive integer n, which could be a polynomial, right? But what if there's only one term? See, like here they have f of x is just, and there's just a single term. That could be called a monomial. Ooh, you guys look at these two words. They have different prefixes. Right? Poly, is many. Mono means one. So if you have one term, then that could be a monomial, right? But if I have lots of terms, okay, we'll flip the next page over here, right? Well, if I have f of x equals 11x to 3 plus 5x squared minus 7x, that could be a true polynomial, like definitely polynomial and not a monomial because I see three different terms there. Right? Now, I am covering up part of what they took. And let me show you guys. Right? It actually ends in minus 6 over x. Now, that violates the polynomial rules. So this would not be a true polynomial because of that very last term. We're dividing by x, or take it x to the minus 1 if you like. Right. So let's look at in behavior rules. They give you this brief table here. So four categories. What if the degree, let's say that the largest power of x is even, right? What if it's odd? And the leading coefficient, what if the leading coefficient is, okay, so here's even and odd. Right? You guys remember even and odd functions from a few chapters ago. What if the leading coefficient is positive versus negative? Right? So the rules are if the degree is even, for example, x to the power of 4, x to the 2, x to the 4, x to the 6, like that, you'll always see this U-type curve that goes up forever in both directions. And the way you write that mathematically is this: as x approaches negative infinity, let's say if you're going left forever, f of x approaches infinity, which means you go up forever. So it goes up to the left forever and ever and ever. Okay? And then as x approaches positive infinity, you're going to the right forever. F of x approaches also positive infinity, so it goes up to the right forever. Okay? And then how about if you slap on an odd power to the make the degree odd. So x to the 3, x to the 5, x to the 7. You could x to the 1 would also work. Right? Look, as f of x approaches negative infinity, sorry, as x approaches negative infinity, you're going to the left forever. F of x also approaches negative infinity, so it goes down to the left forever. And as x approaches positive infinity, f of x approaches positive infinity, that goes up to the right forever. Okay? Now, everything I said so far, this is true as long as the leading coefficient is a positive value. If you make the leading coefficient negative, everything just flips upside down, and now it looks like these. Right, so I put a few of these examples into Desmos. It pull this up here. Here we go. Right, here's a bunch of even look example. So even powers: x to the 2, x to the 4, x to the 6. You can see them all. Right, they all have the exact same in behavior. Whether you go to the left or to the right, you're going up forever either way. Right? What happens if I slap a negative on this? Boink. Oh, it flips it upside down. Let's get rid of that. What if I say plus x to the power of 3? What do you think that's going to do? X to the 3. Right. Well, it still has the same basic in behavior uh, because the leading term, well, I should say the degree is still 6, right? So 6 is still the dominant term. Now, if I change this 3 to a 7, now we should see some significant changes because 7 would be greater than 6, and also it's odd rather than even. So there you go. Now the rules reverse. You see how this is working? Okay. But I could do like x to the 4 plus 5x to the power of 3 plus 5. It doesn't matter. Right? So this green curve right here is what we're looking at. It still has the same in behaviors, all determined by that power of x. So x to the 6 tells you everything you need to know there. Right? And so those are even powers of x. Let's look at some odd powers of x. Oops, odd powers. So boink. Here you go. I got x to the 1, x to the 3, x to the 5. Of course, x to the 1, this red one is just a straight line. That's y equals x. Right? So, for example, the coordinate 2, 2, 3, 3, 4, 4, and so on. Y is x. Right? These other ones bend a little bit, but look, they all go down to the left forever and up to the right forever. If I slap a negative on one, let's take this green one, slap a negative, boink. Oh, now it's upside down. Now it goes up to the left forever and down to the right forever. So that's upside down. And so that's all that table was saying. Right? Just like that. Okay, so we got that. What we got next? In behavior and degree of a monomial function. Okay, so monomial, we're going to get one term. Oh, and there it is. F of x is negative 2x to the 3. Okay. State the domain and range. Okay, so I bet a lot of you guys could figure out what this is going to look like. Let's see, I think I got this on Desmos right here. Oink. There it is, negative 2x to the 3. So here, if it was just x to the 3, it'd go up to the right forever, down to the left forever. By slapping the negative, oink, flips it upside down, okay, up to the left forever, down to the right forever. Now, the domain is the possible x values. X can be anything from negative infinity to positive infinity. And the range is possible y values. Well, this could go up forever or down forever, so y could also be negative infinity to infinity. There's domain and range right there. Right? Uh, Example two, graph a power function by using a table. We got water to flow through a garden hose at a certain rate in gallons per minute needs a specific pressure in, say, pound per square inch. Okay, so we've got two corresponding type variables, right? What's the flow rate and what's the corresponding pressure, maybe to produce that flow rate? Okay, and also the variables attached to each of those, right? Gallons per minute for flow rate and pound per square inch for pressure. Okay, so we found this relationship. Let's say the pressure as a function of the flow rate, or maybe the required pressure to produce some flow rate or something, is 3 over 2 f squared, with these specific variables. Right? Graph the function and state the domain and range. Right. Got 3 x squared. Right. Okay. Glance at Desmos. I did not put that one in Desmos ahead of time, but they do give it to you right here. Right? Maybe here. Here's what I'll do with you guys. Okay. I'll show you guys exactly how to put this table together. Guys, any graph that you ever want to make this, if you have no idea what the graph looks like, or if it's getting kind of complicated or whatever, right, you can always make an XY table. In this case, it's not XY. Instead of X, we have F for flow rate, but that's kind of like X. Instead of Y, we have P for pressure. Right? So let's find a bunch of values. Okay. Now, interestingly, on their table and also in the graph, they are showing negative pressures. Almost like sucking the water in. I guess it could, right? Why not? Right? Maybe it could be like a vacuum or right? So let's go like a negative 2 pounds per square inch. I think this might be referring, or so that's flow rate. Okay, yeah. So now the water is definitely being vacuumed right, into the hose. Right, so right, here should be no difference at all. Right, there's no flow rate. And what if the flow rate's positive? Right, so many gallons per minute. Right? What would the corresponding pressure be? Right? Okay, so back to the point I was trying to make. Any graph you ever want to make, you could just make a table and just plug the values straight into the equation and see what comes out of it. That was true all last module with quadratic functions and parabolas. That was true before that when we were doing linear. Just plug stuff in. So here they're given 3 over 2 times the flow rate squared. Well, my first flow rate is negative 2. I'm going to square that. Make sure that's in parentheses before you square it, because even the negative is squared. I'm getting a required pressure of 6, right, and that'd be pounds per square inch. Yeah, in my physics class, I always emphasize putting on units. So I'll put flow rate in gallons per minute here, right, so that the numbers actually mean something, and pressure is in pounds per square inch. I see that. Okay. I could plug in -1. Let's see what happens. I'm getting 1.5. I can plug in 0. Oh, 0, 0. Right? If you want no flow rate, you need no pressure. Right? I think they're kind of about gauge pressure, so they compare it to the atmosphere. Right, so 1.5 pounds per square inch needed there. And if you want 2 gallons per minute, you need 6 pounds per square inch. Okay, yeah, okay, so actually, this is a parabola, isn't it? Yeah, because look, it's basically y equals x squared, with the leading coefficient of 3/2. Okay. Yeah, and that's exactly what they graph. Look at that. Look at that. So 0, 0, that's that point right there. 0, 0. Okay. How about 1, 1.5? So 1, 1.5 right there. 2, 6. That's that point right there. Right, you could graph as many points as you want. I mean, there's 5 points. Makes a nice parabola. Boom. Okay. Um, Graphing polynomial functions. Okay, a polynomial and one variable is in the form a x to the n. Okay, okay. So when they're talking about one variable, they're talking about one variable x. You see that these all have leading coefficients at different degrees, but the only independent variable is x. I see x there, x there. Okay, so maybe you could have a constant at the end. That's okay, but variable. But you aren't mixing like x's and also n's and some third or fourth variable. No, it's just y is a function of x. That's all. And if you list it from greatest to least degree, so the greatest power, maybe n could be, oh, I don't know, like 5, and then n minus 1 is like n x to the power 4, and then and so on. That's called standard form. And the degree is just the highest power, which would be a whole number, and the leading coefficient is 8n. So that coefficient in front of the highest power. Uh, the highest power bets. A polynomial function is a continuous function that can be described by a polynomial equation in one variable. You learned about constant, linear, quadratic, and cubic functions. Right? Quadratic could be x to the power 2, cubic could be x to the power 3. A quartic function, is a fourth degree function like x to the power 4. A quintic function, x to the power 5. Okay, so quadratic x to the power 2, cubic x to the power 3. Now we have x to the 4 and x to the 5. The degree tells you the maximum number of times the graph of a polynomial intersects the x-axis, or could potentially intersect the x-axis. Maybe it only does once or twice, or maybe some parabolas never cross the x-axis at all. But parabolas can cross the x-axis up to 2 times. Right? So that's why x to the power 2, right? If that's your highest power, if that's the degree, it could cross the x-axis up to 2 times. So if you have, say, a quintic function, x to the power 5, let's say some crazy polynomial, there's a bunch of other terms in there. Right? It could cross the x-axis up to 5 times, is what they're saying. Right. So you state the degree and leading coefficient, and one variable. Right? What's the degree? What's the leading coefficient? No, 2x to the 4 minus blah, 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 all this stuff. Well, I say the degree is 4, x to the 4, because that's the highest power on x. So the degree is 4. And the leading coefficient is 2, because that's the coefficient on the term of the highest power. There you go. X1, 7x to the 3 minus 2. It's degree 3, because x to the power 3. And leading coefficient 7, because that's the coefficient. Right? Now this one, look at here. What if you had z equals 4x squared minus 2xy plus 8y squared? Now, if you graph this, this would be in 3 dimensions. So this would not be a polynomial in one variable. Right? So we'll typically not look at this. Right? There's these 2 independent variables like x and y. Okay. Right. So maybe a real life example is, because I know this is pretty abstract, right? But what if you were trying to make like an optimal cake, right? And you wanted to vary how much sugar should I put in here, and how much flour, right? And you were using those as variables, right? Different amounts of sugar, different amounts of flour, and maybe the z variable, like z equals, could be a function of like people's enjoyment of it. So it's like, well, if I increase the sugar a little bit and decrease the flour a little bit, right? You play all the different combinations, right? There's some cake that's the most enjoyable, right? And enjoyability could be like a third variable, z. So z equals enjoyability equals something as a function of how much sugar or flour you put in. Okay? So there won't be too many of those, because that's not our main focus. Right? Now this next one, I only see x's here. X to the 5 plus 12x to the 4 minus blah, 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 all the way down to plus 4. Okay? We don't even need to know all this stuff to answer this question. This is degree 5, because it's x to the 5 is the greatest power, and the leading coefficient is 1. Ooh, there's an applied 1 here. That's all. Not too bad, right? Example 4, evaluate and graph a polynomial function. The density of the sun in grams per cubic centimeter, expressed as a percent of the distance from the core of the sun to the surface, is modeled by this crazy function. Look at this. F of x equals 519 x to the power of 4, blah, 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 blah. So crazy looking polynomial here, where x represents the percent as a decimal. So if x is equal to 0, you are at the core, because you're 0% away from the center. So x is 0 is the core. Actually, you know what? I can see what it is before doing any calculation. The density would be 155, was this grams per cubic centimeter at the core. Well, according to this equation, it would be, right? Because if x is 0, you're just left with 155, right? Now, you can go up to the surface x equals 1. I suppose that would be the domain, right? If that question pops up, what's the domain? Well, the domain would be between 0 and 1. Because by the time you get to 1, you're at 1 unit of the radius. You're at 100% of the radius of the sun. Right? And anything beyond that, well, you've left the sun. So this equation shouldn't count anymore. Okay? Evaluate the function, find the density of the sun. Let's say it's 60% of the way to the surface. Right? X represents the percent at, it says as a decimal. So I think 60%, I would want to interpret that as 0.6. Yeah, that's look okay. That is what they did right here. They just plugged in zero point 0.6 to this crazy looking equation, and then their table values they set up where it goes from like zero point 0.1 to zero point 0.9. Okay, that makes sense. Okay. They're coming up with this looking graph right here. Right? See, all they did was they just over and over plug in points. Here, I'll plug in at least one of these for you guys. You guys can see this. Okay. Okay, so if I do 519, here, I'm going to do the trick that I showed you guys a while back, or I've been showing you guys a few times. In place of x, I'm going to hit second to answer, and I'll let that stand for x. To the power of 4 minus 1630 x, that'll say answer, and that's to the power of 3, then plus 1844x squared, then minus 889x plus 155. Okay. Now, first when I hit enter, I'll just get the junk answer. It doesn't make any sense. Okay. But what value of x do I want? Okay, let me do one that they already plugged in so I can confirm that everything's correct. Right, you guys can see exactly this one. So if I hit 0.4, right, and then hit enter, okay, now my calculator is saying, okay, something with like 0.4, or something with 0.4, right? Okay. And remember what that means. That means 40% of the way to the surface from the center. Okay, so we're like almost halfway to the surface from the center. Okay? Now scroll up twice, and the calculator will automatically plug in that 0.4 everywhere it says answer, and I should get 3.4 if it does it right. Yeah, yeah, look at that. It matches exactly. It's the same thing. Okay? Now the question here was what about 60%? So I'll type in 0.6, then scroll up. Okay? And the answer to this question is going to be 0.62. Here, I'll go ahead and write that in here. 0.62, right, and a string of numbers, 224 grams per cubic centimeter. Okay? Now you can plot this, right, with the densities, percent of radius that goes from 0 to 1. Right, so I threw this into Desmos also. Uh, see, I don't know if I made a typo or something, but so don't double check what I typed there. Plus 155. Yeah, okay. I think this goes on for a while. Yeah, okay. I think that's all there. It's not the same thing, right? Because this graph looks a little different. I don't know, it goes negative for some reason. I don't know about what that's about, right? But it does have okay, guys, you guys see this plus 155? So if you plug in 0 for x, just say you were at the core, I made a claim that the answer should be 155 where x is 0, because all this zeros out. Let's see if I zoom back far enough. If I zoom into 155, I think this should be the y-intercept, right? Yeah, there it is. Right, it's giving it to me. Right, 0, comma 155. There you go. So that's like the y-intercept, which tells you the density at the core. Ooh, something like that. All right, so basically that. All right, shuffle this one off. All right, boing. See what I got. It's lined up here. So very close. All right, so here we go. Pretty good. Um, all right. This one. Example 5, zeros of a polynomial function. So you guys know what zeros are. That's the x-intercepts. It's just a math term for x-intercepts. So if you set the whole function equal to 0, you're saying, what can I plug in for x to make the whole thing equal to 0? And I see three values on this graph. Boink, boink, boink. So if they give you the graph, you just take it straight off the graph. Right? So it looks like at -2, at +1, and +4. So those particular x values. Oh, yeah, actually, that's exactly what it says here. -2, 1, and 4. So at those particular x values, it would zero out. How about this one down here? This one I see four zeros. Point, 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 point. So if I wrote each of these like in equation form, say in my standard form, I know this would this top one probably have a degree of 3, something x to the power of 3 plus blah 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 blah. You might create a graph like that. And this one probably x to the power of 4, like x to the power of 4 plus blah 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 blah. It probably create that sort of W looking graph right there. Okay. Like that. Because remember the degree tells you the maximum number of times it's allowed to even cross the x-axis. Crosses the 3 twice here, it's got to be at least x to the 3, and then crosses 4 times here, it's got to be at least x to the 4. Ooh, all right, last example, then we can jump into the ones that I highlighted here. Examine x to the 3 plus 2x squared minus 3x. X squared minus 3x. Okay, I think say I put that in Desmos here too. That okay, I think okay, that's this f of x here. Okay, so this f of x is this f of x. So they set you up a partial table. They're saying, hey, what if we plug in different values of x? What do we get for y? And it creates this graph. Okay. Uh, this I want you to compare it to why do they have g of x here? Okay, yeah, which function has a greater relative maximum. Okay, here's compare polynomial functions. So comparing this f of x, which they gave this equation and part of this perfect table and this graph, this all goes together. They're comparing that to this g of x here. Okay? Right, so which one has a greater relative maximum, for example? Well, now we're talking about relative maximum. Remember, that's different from absolute maximum. Like both of these graphs continue up forever. So they both go to positive infinity in terms of the range. Right? I think when they say relative max, they're talking about this local extreme. Like if you compare this one to this one. Now, this f of x goes all the way up to 6. This g of x only goes up to about 2.5. Well, 6 is more than 2.5, so this one would have the greater local maximum. Right? And what about local minimum? Well, this f of x goes about negative a half-ish, somewhere there, and g of x goes all the way down to about negative 2.5. Okay, so this one goes even lower as a local min. Right? But again, that's just a value of local min. The f of x does go down forever, if you want to consider that too. Right? But maybe not as a relative min. All right, let's jump into these highlights here. Describe the end behavior of each function using the leading coefficient and degree, and state the domain and range. All right. So I'll write these down here. So number 2. Let's see, we're looking for uh, leading coefficient. Looks like negative 2. And degree, that's just the power on x, which is 3. Yeah, that's all. Okay, and then domain and range. So domain, here, I'll use a set builder notation. How about that? How about x such that x, well, I don't see any reason for any restriction on that. X could be anything. I could go from negative infinity to infinity. So I'll say element of all real numbers. You guys remember that? Element of all real numbers. There's my set builder notation for. Right, and then range, I could do uh, well, since it's an odd power, the range could also be anything. Right? So I think it'd be something like this: y such that y is also an element of all real numbers. Right? And in interval notation, that might look like this: negative infinity to infinity on the domain, and same thing for the range: negative infinity to infinity. Different notation for the same idea. Right? Here, I'll go ahead and throw that into Desmos. It's okay, boing, Desmos. Okay, yeah, I got that queued up right here. Negative 2x to the power of 3. Yeah. See how this could go up forever, down forever, left forever, right forever? Okay. So negative x to the 3, okay, up to the left forever, down to the right forever specifically. But there's no restriction on either the domain or the range. Okay, so got all that. Yeah, boink. All right. What's number 4? All right, so same premise. All right, we've got 3/4 x to the 6. All right, so I think the leading coefficient would be 3/4. The degree would be 6. Okay? The domain could be x such that x is an element of all real numbers. Right? I don't see any reason for a domain restriction because you plug anything in this. Now the range is going to be a different story. Range. I'll say y such that y. Well, right, you get plug anything in for x you want from negative infinity to infinity, but you won't get anything for y. If anything to an even power, doesn't that only produce positive numbers, positive real numbers? Right? Now you could get 0. If you plug in 0, you'll get 0. Right? But there's no way to get any negatives out of this. So I'll say y is greater than or equal to 0. Right? How about interval notation? So domain, of course, negative infinity to infinity. Okay? Now the range picks up at 0, so do you bracket 0 and can go to infinity. So it's a different notation for the range. Like that. Okay. I think I threw this into Desmos. Let me see if I did ahead of time. Um, yeah, 3/4 x to the 6. Looks like it. Okay. Okay, there's a picture that would have been good to have too, right? Okay. So see how x could go left forever, right forever. There's no restriction. There's no vertical asymptotes, nothing like that. Right? It just takes off real fast. But in terms of the range, it only goes down to 0 and it can go up forever. So there's a range restriction. Here, let's get rid of this. Boink. Bye. All right, that's 2 and 4. Number 5, use a model. The shape of a parabolic reflector inside a flashlight can be modeled with the function f of x is 4/3 x squared. Graph the function, state the domain and range. Yeah, here, let's make a whole table and whatnot with this. Oh, hey, isn't this a parabola? Didn't we just spend like 3 weeks doing module three, and that was all parabolas? I said x value, y value. Let's make this that. So how about instead of what? Wait, state the domain and range. No, okay. Let's go to -2, -1, 0, 1, 2. Okay, get some points out of this. Okay. I'll use that trick I was showing you guys. So 4/3 answer squared. Okay. Okay. Let's plug in -2. Scroll up. Okay. And it's telling me 5.33. Here. Oh, I'll round to the nearest hundred. Say I'm allowed to do that. -1, 1.33. 0, of course, I'll get 0. Okay. And then 1 and 2, well, I'll get the same values as these because it's to an even power. So it has to be symmetrical. I think this would be called an even function. An even function. You guys remember even functions? Okay. So let's graph this thing. All right, so yeah, here's x, here's y. Okay. So it went from -2 to 2 in terms of the domain. Now the range goes up to a little over 5. Here, I'm going to swash this y-axis a little bit. Let's go 1, 2, 3, 4, 5, 6. That's 6 up there. All right, so we got -2, 5.33. It's we got there. -1, 1.33. 0, 0, 1, 1.33. And 2, 5.33. Yeah, I'm getting a parabola out of it. Yeah, getting a parabola right there. Look at that. A squash parabola. Okay. That is spelled the function f of x, or y if you like, equals 4/3 x squared. Yeah, just like that. Now, domain and range. I guess realistically, like if this was what a flashlight looked like, right? So you have the bulb and then this mirror surface and it reflects it, so it's a cast a beam of light. Right? Look, guys, next time you pick up a flashlight, look at that. What you'll see is like there'll be some bulb here, like this, got some little filament inside it, whatever. Right? This lights up, right? And it'll reflect off this mirror and it'll shine the light in a certain direction, like a beam. That's what that's for. Right? I think realistically, the domain and range would be like the width of the flashlight and how deep is the flashlight or something like that. But mathematically, I think it would just be all real numbers for both the, or well, all real numbers on the x and then 0 to infinity for the y. And we just did one that's kind of like that. So I'll just go ahead and move on. All right, what's next one here? Number 6, machine efficiency. A company uses this function to model a change in efficiency of a machine based on its position x. Right. So maybe this machine can move left or right. And if you have it centered, it has some efficiency. As you move it left or move it right, there's some change in efficiency. Oh, okay, so let's get that. So let's go f of x, then spell it there, equation here, equals, we got x to the 3 plus 3x squared minus 18x minus 40. It said graph the function, state the range. All right, so uh, you know what? Here, let me throw this into Desmos first. I mean, did I do that already ahead of time? Got x to the power of 3 is 40. Yeah, okay. Actually, I got that right here. Boing. All right. Let's take a look at what this looks like. Okay. So I'll have Desmos do it first, and then we'll figure out what. Okay. All right. So it looks like if the machine is centered on like some center place, right? Maybe it has some efficiency, right? And maybe as you move left, it looks like the efficiency increases up to what, like 17 units there, or whatever. And as you move to the right, it looks like it loses efficiency in a hurry. Like that. Change in efficiency, huh? Did I really have the? Okay. Um, no, guys, the fact that this has a degree of 3, which is an odd degree. I know this graph will eventually go up and to the right forever and down to the left forever. So its domain and range would each go from negative infinity to positive infinity. Right? There's nothing that either x or y could never be. Right? Right. So, but show you guys how to plot some values. Let's make an XY table and figure out what from here. So different values of X, different values of Y. Actually, we pull up that Desmos again real fast. See if I zoom way in. Let's get some reasonable type values. Okay. Here, I'll try it. How about
-5, -3, 0, 3, 5, something like that. Um,
Okay. Let's go -5, -3, 0, 3, 5. Okay. Of course, the more points you plot, the more accurate it's going to be. I'm just showing you guys an idea, right? Based how you just. So we got answer to the 3. So x to the 3 plus 3x squared minus 18x minus 40. Right? So if I plug in -5 and plug that in, oh, was it -5? Did I really pick? I don't think I meant to do that. -5, 0? Oh, yeah, okay. Actually, that is a point. -5, 0. Oops. Okay, that's all right. -5, 0. Okay. Um, yeah, you know what? Let's make a whole table of values. I'll show you how to do this real fast. -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Okay. We're gonna run all these. Ha 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 ha. Run all these. Okay. Okay, so if I plug in -4, scroll, plug it in 16, -3, 14, -2, 0, -1, -20, 0, -40, 1, -54, 2, -56, 3, -40. Ooh, come back up. 4, 0, and 5, 70. Boom. Just knocked out all those coordinates right there. Okay. Oops. Okay, so in my table, okay, I went from -5 to 5. So let's mark that up. Give myself an x-axis, a y-axis. 1, 2, 3, 4, 5. So -5. 1, 2, 3, 4, 5 that way. And this goes from -56 to +70. Let's go -10, 20, 30, 40, 50, 60. 10, 20, 30, 40, 50, 60, and 70, something. Okay. Let's follow this one. It's -5, 0. Point -4, 16. Well, that's 10. It's probably right about there. -3, 14. It's probably right about there. -2, 0. -1, -20. 0, -40. 1, -54. 54. 2, -56. 3, -40. Okay, got that. 4, 0. 5, 70. Yeah, you could definitely see the shape emerging. Look at this snaky looking shape right here. Oh yeah, we're getting a third-degree polynomial. We go on forever that way up to the right, go forever this way down to the left. That's it. Here's your graph. Done. Okay. Domain -infinity to infinity. Range also -infinity to infinity. Got some light eyes. Um, So it's number 8. State the degree and leading coefficient of each polynomial. If it is not a polynomial in one variable, explain why. Okay. Right, so 8. Ooh, this looks like they give it to you in factored form. Now, this factored form could be useful because you can very quickly spot one of the. Actually, I think this one has one like 0, like one x-intercept. And that's where x is 1/2. Because look at this, 2 times a half is 1. 1 minus 1 is 0. That 0 got the whole thing. Okay. And this other one, if you get x squared plus something, well, that'll never give you any real zeros, maybe imaginary, but not real zero. Okay. I kind of remember that from the last few weeks. Okay. Uh, okay, but this is not in standard form. So let's put this in standard form. So I'll say y equals, let's go 2x minus 1, 4x squared plus 3. Never quite seen anything like this in this class so far, I don't think. And so now we can still FOIL this. Let's go first, outside, inside, last. Okay, so we're still using FOIL rules. First, outside, inside, last. Okay? We're going to get a little different outcome because this is x squared. So our first term is actually going to be x to the power 3. Ooh, 2 times 4 is 8. So that's the same thing as 8 because 2 times 4 is 8. X to the power 3. Because, if you multiply x by 2, you can add the exponents. X to the 1, x to the 2. Okay. Right, then outside. Actually, let's do inside first because there's an x squared there. Let's do inside first. So that's negative 4x squared. Then we'll throw in the outside, which is 6x. And then finally, last, negative 3. Okay. Okay, so this is the polynomial in standard form. I'll spell it out. Standard form. When you have it in standard form, you can answer the question, which is what's the degree leading coefficient? So it has degree of 3 because of this right here. Boing. And the leading coefficient, coefficient is 8 because of that right there. Bing. There you go. That's all. Uh, Number 10. Ooh, what is this? We got something in terms of y. You guys notice there's still only one variable that's given. So this is still a polynomial of one variable. I might say something like this. I might say z equals, or like f of y if I wanted to. Now I'm going to rearrange this. See how they put the highest power at the end? Right? That's not super conventional. So I'm going to reverse this whole thing. I'll say 7y to the 6, which I'm getting right here. We got minus y to the 5th. I've got plus 5y squared minus 3y, and then there's a plus 18. Okay? So all I did was I just reversed the order of the terms, but it's still the same function, right? Okay? Now z is a function of y, so I can make the z-axis and y-axis. I can still make a table, like a yz table, and plot all the points and make a graph. Okay? And so this one has degree 6 from right here, bing, and leading coefficient uh, coefficient of 7. Okay, that's wrong right here. Bing, there you go. Degree leading coefficient. Wait, number wait, no, 11. Hey, look at this. 11. Here. Now we got u's and t's. Yeah, maybe we'll say y equals or something like that. Right? It's u to the power 3 plus 4u squared t squared, right? Plus t to the 4, right? Okay. Remember earlier, I was saying an example of like, what if y is like enjoyability of cake? Okay, and you're the baker, and you got two variables that you're playing with. Maybe u represents the amount of sugar, so I'll say amount of sugar, however you measure that in cups or whatever, sugar. Right? And look, okay, that could be that u and also that u. Okay. Let's say t represents the amount of flour. Right? So I'm just making a real life potential example of something like that, where you're playing with sort of two independent variables and saying, how does that affect this third variable, like the enjoyability, right? So I can add or subtract more flour or sugar, and there's going to be some like optimal cake, right? Well, guys, this would not be a polynomial in one variable because there's a u and a t, right? There's sugar and flour that we're messing around with. Right, so yeah, I think we're done with that one. Right, done. Next. And number 12. Okay, now this is one variable. The only variables are, but this one does look different. Here, so I'll say y equals, okay, I got 2r minus r squared plus 1 over r squared. Okay, well, this right here, 1 over r squared is the same thing as r to the negative 2. Now, whether you have fractions or negative powers, which are the same thing, this would make it not a polynomial. So not a polynomial because of this right here. Bing. That's why it's not a polynomial. Okay. When we start off, okay, those first two terms could be polynomial, check, check, check. And we get, okay, not because of this. Fail. Number 13. 13. Triangles. We've got Dylan drew in dots on a piece of paper, making sure that no set of 3 points were collinear. Okay, so there are no 3 points that are all in a row. Okay. And if that's true, the number of triangles that can be made, that's an interesting function. So the number of triangles is a function of the number of dots. Write this out. Okay. So the number of triangles as a function of the number of dots is 1/6 of number of dots to the power of 3 minus 3n squared plus 2n. Okay. Again, as long as none of the dots are all in a row, which is called collinear, so you can't draw a straight line through three dots or one. Um, okay, where n is greater than or equal to zero, so you have to have, well, you can't have a negative number of dots. Okay. If Dylan drew 15 dots, how many triangles can be made, and then sketch a graph? Okay. So let's answer this question first. And I think I threw this in the Desmos at that time, so we'll see. Okay. So question A, what is basically f of, let's say 15? Yeah, 15. Okay. So if you threw 15 dots on a paper, here, this might look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, actually, assuming you, let's try and make them not, let me make them bolder. Right, 1, 2, 3. I want to make sure I don't put any that are like three all in a straight line. Okay, that's getting a little too close there. But to kind of curve this around a little bit. Maybe try to definitely avoid dots in a straight line. Okay, maybe something like that. Something like that, where none of these dots can be all three in a straight line. Okay, okay. So how many potential triangles? So what are they talking about? Well, you can make a triangle like this. Okay, like that could be a triangle. Okay, okay. And since there are no dots that are like three in a row, then you don't have to worry about accidentally making straight lines. Right, so like that could be a triangle. Right. Ooh, how about from here to here to here? Like that could be a triangle. Right. There's three triangles. Right. One, two, three. Right. I bet you could use some points again. So what if you did this point and this point and connected it with this point? Ooh, there's a fourth triangle. Right. I wonder how many triangles can make 100 triangles? Could it make 1,000 triangles? Well, this equation will answer that question. How many total triangles can it make? So 1 over 6 will go 15 to the 3 minus 3 times 15 squared plus 2 times 15. Okay, just pop that in the calculator. We're going to find out. So 1 over 6, 15 to the power of 3 minus 3 times 15 squared plus 2 times 15. All right, I'm looking at 455. So the answer is, if I connected all different combinations of dots, all ways to make as many triangles as I want, there are potentially 455 different triangles. Okay, there you go. And wait, what else did I ask? Okay, sketch a graph of the function. Okay. Now, I see this is a cubic, right? You guys see like n to the power of 3, something like that. And so I know what basic shape is going to be. Go to Desmos. Was 3x. Okay. Yeah, I think it's this one right here. Point, make sure. Yeah. Yeah, that's it. Right. So, okay, we're zoomed in real close because if you have zero dots, you can make zero triangles. If you have one dot, you can still make zero triangles. If you have two dots, you can still only make zero triangles. Right? If you have zero, one, or two dots. Now, as soon as you get a third dot, I bet you can make exactly one triangle. So is that true? Yeah, yeah. Guys, look at this point right here. Isn't this 3 comma 1? So if you have three dots that are not collinear, make exactly one triangle. Right? What if you throw a fourth dot in the mix? Right? So what is this point here? I guess 4. I guess you can draw 4 potential triangles, 4 dots. Right? And then they asked for like 15. And I got like 455, which is just like, okay, way up here. Okay, something like that. Yeah, but that looks consistent with what we were just doing. Looks about right. So we are good. Yeah. So yeah, I think we worked it out. Okay. I think we got three quick ones here we can knock out real fast. So 15, 16, 17. 15, 16, 17. Okay. State the number of real zeros. Okay. Remember, real zeros is the number of times it crosses the x-axis. And I see one right here. So the answer is 1. There's only one real zero. Okay. Now this one, I see 1, 2, 3, 4. So there'd be 4 real zeros. Okay. Um, this first one is linear here. So I'll say, for example, this might be like y equals uh, x minus 3, for example. That might be y equals x minus 3, right? Y equals x, it's a 45-degree diagonal line. Shift it down a little bit, boom, looks like that. Okay. Okay. And then I bet this would have to be y equals, now I see it's sort of like an upside down W looking shape, or maybe an M shape. Okay. I bet the leading well, term has to be some version of this, negative x to the power of 4, but it has to be more than that because otherwise it would never come back and cross multiply. So it does have to have a bunch of other stuff added to it. Like maybe there's an extra 3 term and so on, but you could somehow make something look like that. And then how about number 17? I see 1, 2, 3 places it crosses the x-axis. Now, interestingly, it does dip down like it wants to cross again, but it didn't quite make it. It turns around again. So, uh, you see how x to the 1 has just one straight shot, and x to the power 4 at least has 1, 2, 3, 4. Well, this has 1, 2, 3, 4, 5. So I bet this has to be at least y equals, okay, and it would be negative, goes up to the left and down to the right. Negative x to the 5 plus, and it has to have a bunch of other stuff added to it. But I bet the leading term, or yeah, it looks some version of that, to make the shape. Okay. All right, but all they were looking for was how many zeros, how many x intercepts to say. All right, so did that. What have we got next? These right here. Oh, describe the in behavior, state the degree, and leading coefficient. Okay. So, right, 26. And if the function is not a polynomial, we'll explain why. So maybe one I picked out is possibly not a polynomial. So h of x equals 9x to the 6 minus 5x to the 7 plus 3x squared. Okay. Now, to answer this question, right, what's the degree, leading coefficient, and in behavior, and so on? The only term that matters to all those questions is just this one right here. All you have to do is look at that. Okay. So I see degree 6. I see leading coefficient of 9, right, from right there. Right, so we're just doing this number, point, this number, uh, point, right there. Okay. And how about in behavior? In behavior. Okay, so here, the notation that they're using, uh, this could be helpful in, oops, in calculus. Right? Uh, in calculus, this is called limits. So as x approaches something, f of x approaches something. Okay? So here I'm say as x approaches, let's go to the left forever, negative infinity. Okay? Now, see how it's an even power? I know the graph basically does something kind of like this. Okay? Now it might do something uh, like this, right? Like that could also possibly be the case, right? But it's got to go up to the left forever and also up to the right forever, right? So that'll be the indicator. So I bet it looks something like either that or that. Uh, um, so as x goes, here, what's the rest of their notation here that they use? Uh, okay, all they did was comma and then h of x in this case. H of x approaches positive infinity. So if it goes left forever, you're going to go up forever. As x approaches positive infinity, h of x still approaches positive infinity because it goes up to the right forever. That's all. Okay. All right. A couple more of these. 28. Right? I've got f of x equals 5 minus 2x and 4 plus 3x. Ah, this is back to a parabola, isn't it? Back to a parabola. Okay. In fact, I can whip off a graph real fast because I can pretty much immediately see what the zeros are going to be. Like 5 minus 2x is equal to 0. That could give you an x of like 2.5 because 2.5 times 2 is 5. 5 minus 5 is 0. So where you have 1, 2, 3, like 2.5, there's a 0 right there. And also where x is negative 4 over 3, which is right about here. Because negative 4 over 3 times 3 is negative 4, plus 4 is 0, so that would 0 up. Okay? And this is going to be a parabola. I'm going to FOIL this out. I do have to FOIL this out to do the rest of this. Okay? But this is what the graph looks like. That's it. If you open up Desmos and type that in, it would create that graph. Okay? Something like that. All right, now here, I'm going to FOIL this out though. So I'm going to say this is equal to, let's do, here, right here for getting strong. First, outside, inside, last. FOIL. FOIL. First, outside, inside, last. So excuse me, 5 times 4 is 20. Outside is 15x. Inside is negative 8x. And last is negative 6x squared. Okay? Now we can clean this up a bit. Right? We can combine these two terms because they're both x terms. And also, I'm going to rearrange this to put the highest power of x, this term in the front. So here, I'll write down here. So f of x equals, I got negative 6x squared. You know what? Right. I just realized something kind of funny. Right. I forgot my negative here. So it does have these x-intercepts, but actually I do need to turn this graph upside down. Right. Oops. Let's do that. It's actually going to look more like this. Okay. Yeah, I'll get rid of that original one. Okay. So I got the correct zeros. So I just I missed that negative point right there. But now that I foiled this out, that stood out. It's like, oh, okay, actually, whoops, that would be upside down. Let's just see that. I said, there you go. There's a better looking graph right there. Like that. So we got the x terms combined is plus 7x, and then I got a plus 20. Right, there you go. Right. Now, what are we looking for again? The degree and leading coefficient. So this is degree of 2 because of this right here, which is also called a parabola. Leading coefficient is negative 6, which is right here. That's what tells you the whole graph just turned upside down, the whole parabola turned upside down. Okay. And end behavior, end behavior. Okay. Now for that, I'm going to say as x approaches negative infinity, if you're going to the left forever, well, you're also going down forever, so down to the left forever. So comma, f of x approaches also negative infinity. I said left forever, goes down forever. As x approaches positive infinity, f of x still approaches negative infinity. Because look, as you go to the right forever, you still go down forever. That's what an upside down parabola does. There you go. Here's all of it right there. Now, number 30. Okay, we've got g of x equals 3, x to the power 7, okay, which makes me think down to the left forever, up to the right forever, minus 4x to the 4. Oh, what is this? Plus 3 over x. Well, that throws a monkey wrench in this whole thing, because that's no longer a polynomial, because this right here. So number 30 is not a polynomial. You guys saw an example of that earlier. Right? So, hey, 3 over x, wouldn't that actually give a vertical asymptote? No, yeah, this wouldn't even be continuous everywhere. Okay, so this would have a discontinuity at x equals 0. Yeah, so this is not even a polynomial. So we're done with that one. And let's see, I highlighted one more. I'll do one more with you guys. Number 35. I definitely wanted to do some kind of geometric type word puzzle with you guys. Okay. Got a box with a square base with sides of 10 centimeters and a height of 4 centimeters. Okay, so draws approximately to scale. I bet it looks pretty close to this, doesn't it? Okay. We got a box that's at 10 centimeters by 10 centimeters with a height of just 4 centimeters. Okay, so there's your box. For a new box, the height is increased by twice the number x, and the lengths of the sides of the base are decreased by that side x. Right? Write a function to represent the volume in the new box. Okay, well, let's get a kind of a picture here. Okay, so if I start off with that box, here, I'll try as best I can to replicate that picture. Okay. Okay. And then in peeking here, maybe I'll say, what's the change? So, okay, something to do with this variable x, right? It says the height is increased by twice some value x. Right, so let's say this is x and this is another x. It could be a 2x. Right, so we're bringing this whole box higher by 2 notches. Okay? By 2 notches, we're raising up the whole top box. Ooh, now it's a really tall box. Ooh, right? But at the same time, we're decreasing each side by some value x. Right? So this is getting smaller, and maybe it's getting smaller this way also by some value x. This is getting x, it's getting x, and this is getting 2x. Right? I might even call this actually negative x because I'm making each side shorter. Right? So now I actually got like this base plane here. Right? Now it is taller. The whole thing's still taller. It's just shorter. Okay. So that's going to give us this basically right here. Right, there you go. Right. All right. And they want a volume. It's like I sort of hash this in so we can really focus on this peak box. Okay. That's the original height of 4 plus 2x. Okay. So this whole height right here, here, that's not side right. Okay. I'll say h height equals the original 4, this was 4, plus this 2x. So it's this 4 plus the 2x. Right? And this width right here, I'll call this w for width, equals, well, it started off as 10 minus some value of x. Okay? And same thing over here. This is also width equals 10 minus x. Right? So that's what we're looking at. Right? It's 3D box. Right? So the volume box, is that what they wanted? Right. And graph a function. Okay, so we'll do both. I'll open up Desmos too. Okay? To represent a volume of the new box. So volume is a function of x equals, well, isn't that base times width times height? Right? So I got w times h. Okay, that's not strictly in terms of x, right? But I can substitute these expressions in. So I can say the width is now, well, it started off as 10 units, but minus x. Right, now, the whole base is a square, right? The length and width are doing the same thing, so I can just square that. Right? So this times this. Right? And then this height right here is 4 plus 2x. Like that. Right? There you go. There's the volume as a function of x. Right? So I think I can FOIL this out. Right? So let's go first, outside, inside, last. Okay, let's go like that. So that's 100 minus 10x minus 10x minus 20x. And then negative x squared is plus x squared. This whole thing is times 4 plus 2x. Okay? Now we have to do sort of a superfoil. Right? So this 4 gets multiplied by all three terms, and this 2x also gets multiplied by all three terms. Okay? So I think we're going to get 6 terms, and we might be able to consolidate some of those. So volume as a function of x is, let's see, that's 400 minus 80x plus 4x squared plus 200x minus 40x squared, and then plus 2x to the power of 3, because it's 2x times x squared. That's right. Okay, so there's 1, 2, 3, 4, 5, 6. 6 terms right there. Okay. And some of these I can consolidate. Like here's a couple of x terms, and here's a couple of x squared terms. So here we're going to do that. Okay. So volume is a function of x. Also, I'm going to reverse order this. So we'll start with my I'll start with 2x to the power of 3, right? Because that's the highest power on x. So 2x to the power of 3. Then I have x squared terms. Well, 4 minus 40, that's like negative 36, right? And that's x squared. Then I have 200 minus 80. I think that's plus 120, and those are x's. Finally have the plus 400. Like that. Yeah. Here. So that will be the function. Great. And then great. Let's throw that into Desmos to see what the graph looks like. Now you could, of course, make a table. You can make an XY table and just plot a bunch of points. I'll go ahead and throw this into Desmos so you can see. And then what dimensions would produce the greatest volume? I bet that would show up as a some kind of relative max, maybe something like that. Before I throw this into Desmos, I do see that there is a domain restriction on x. Can't x only go up to 10? Because guys, once you subtract 10, right now the width is all the way down to 0. Well, I wonder what it's going to look like in Desmos. Right, let's go ahead and pull it up. Let's see. All right, so Desmos. Okay, so this one I did not graph ahead of time, but we're gonna find out together. What does this look like? All right, so I'll say y equals got 2x to the power of 3 minus 36x to the power of 2. That's plus 120x, and then finally plus 400. Okay. You could, if you want to, also write this like before I even expanded this out, I had it written in a different form. So look at that. Hey, look at this! Look at this! Look at this! Yeah. Remember I said x can really only go up to 10, but I was thinking in terms of this equation. Like if I just saw this equation like out in the wild, out of context, I said, well, x there's no domain restriction. Like x could be 1,000. There's nothing wrong with that.
Right. Okay, but now I see on the graph why this totally makes sense. Because guys, didn't I just point out in the picture? I said once you subtract up to 10 centimeters from the 10 centimeter side, or whatever the unit was, yeah, it goes down to zero, and so the volume would be zero. Right. So it totally makes sense that actually this graph would have to cut off right there, and that should definitely be zero, and it is. Right. So that's nice. Right. See, if you don't subtract anything at all, the box did originally have a volume of. Well, let's see what is the original volume. So back to the beginning. Wasn't it 10 by 10 by 4? It's 100. It's 400. So if x is 0, if you don't change the original box at all, you should get 400 units on the volume. Let's see, is that true? Uh, okay, my equation says it's true because look, if you plug in 0 for x, you do get 400. So that's a good sign. But I'm really just trying to confirm that right here. Is this a y-intercept? Yeah, it totally is. Like that 0 comma 400. Right. Right. But what's the possible maximum possible volume? Right. It looks like right here. Look at this. It's a local extrema. Okay, if I set x to 2, right, so I'm subtracting 2 units from each side, like the length and the width, but also the height is getting added to, right, by 4 units, because remember it was like 2x, right? Right. So if x is 2, that will maximize the volume of the box. And it maximizes at 512 cubic units. Was it cubic centimeters? Okay, actually, it was in centimeters. So yeah, 512 cubic centimeters is the maximum possible volume. So 2512. Right? Right. So to spell it out. But new dimensions. Okay. So uh, I'll say max volume at 2. Wait, double check. It was 512, wasn't it? 2, yeah, 2, 512. Okay. Okay. So that's to say at x equals 2, that'd be centimeters, volume equals 512, and that's cubic centimeters. Okay. And the dimensions, because they said, what are the dimensions? Would be, right, well, see, if we plug in 2 for x, okay, it's 10 minus 2, isn't that 8? Right, so it'd be 8 centimeters by another 8 centimeters. Because this is also the same, so it's a square base, right? So we got 8 here, we got 8 here, 10 minus 2, 10 minus 2. And the top, well, okay, remember, top started is 4, we're adding 2x. So if x is 2, 2 times 2 here would be 4, plus that 4 is 8. Okay. Oh, oh, I should have guessed that ahead of time. Because look at that, actually makes a perfect cube. Yeah. Guys, if you want to maximize the volume of your box, it has to be a box shape. Actually, the answer was always a perfect cube. Yeah, you should have known that from the outset. And actually, if you want to get it even better on that, if you're limited with like some surface area materials, you want even more volume, you could actually squish it into a spherical shape. Okay, so the closer you get to a sphere, this is as close you get with like a box. Right there. Let me give you guys a little bonus tidbit right here. Okay, so here's a calculus bonus. I can show you another way to optimize this. So I'm going to copy this function right here. So volume is a function of x. Here, let me write that down. Let's call this, I'll write this as peak so it stands out. Calculus bonus! Exclamation. Oh yeah. Let's put a little, oh. Right. Equals, okay, so 2x to the power of 3 minus 36x squared plus 120x plus 400. Okay. Now, the idea of calculus is it has to do with rates of change. So if I go back to that Desmos graph that we were just looking at, Desmos graph, this right here, right? If you want the maximum box volume right here, in terms of calculus, what you say is, well, if I hold my pencil or my ruler flush to the curve, it does have 0 slope at any maximum point, which would include this point right here. Okay? It also, by the way, includes okay, this point way down here, that would be the minimum. Okay? We can find both those points, both those extrema, both the top and the bottom, by taking a rate change of the equation, because isn't that what slope is a rate change, and setting that rate change equal to 0, then we can solve from there. So let me show you guys kind of how to do that. So let's say the change in volume is in terms of x, right, is, all right, now there's a funny calculus process you do.
if you guys take calculus, you'll see this. You always take there's a way to take rate changes of polynomials. You take that power, you put it in front, so 3 times 2, the 3 to 2 combined, that gives you 6. Then you subtract 1 from the power. Same thing here. So leave the minus. Okay. 2 times 36 is 72. X to the power 1. This is x to the 1. So that'd be plus 120. Okay. And then the constants always go away. So just go away. Okay. Now I do see all these numbers are multiples of 6. So let me go ahead and take the 6 out. X squared minus 72 on 6. 12x plus 20 equals 0. And you remember from the last few weeks, I think I can factor that. Let's see if I can. There are two numbers that, let's see, multiply 20 out to negative 12. Oh, how about negative 10, negative 2? So x minus 10, x minus 2, right? First, ding, outside, inside, ding, last, ding. Yeah, okay. So this rate of change could go to 0 at x equals 10 and also x equals 2. Okay. Now, you saw on the graph, the Desmos graph, that this would show a minimum and this one showed a maximum. Okay, I mean, okay, it's a little more of that process, but I want to show you guys that there is actually a different way to also get there, other than just looking at the graph and picking the highest point. There's more like formulaic way to do it that, yeah, it's half page paper. Okay. All right, so there you go. That is a wrap on
Lesson 4.1.